Now let's take another example for the chi-square test of independence calculation, and this example is about diet and health status of individuals. So information about the diet and health status of individuals was recorded, and these are the observations. And as you can remember, we had previously discussed these observations in the illustration of contingency table. So again, I'm repeating the same information. So what are the two rows about? The two rows are about one variable, which is the type of diet. And there are two types of the diets: the American Heart Association recommended diet and the Mediterranean diet. So the variable which is presented in rows is the type of diet, and the variable which is presented in columns is the health status of individuals. And there are four categories in this variable: cancer, non-fatal heart disease, fatal heart disease, and healthy individuals. So these are the observations that we have. Now the question is there any association between diet and health status of individuals? Or put it another way, is the health status of individuals independent of their diet? So this is the question that we have. So what is our next step? We have to state the null hypothesis and the alternate hypothesis. And these hypotheses are: the null hypothesis is there is no association between diet and health status, and the alternate hypothesis is there is an association between diet and health status. So these are our hypotheses. So what is our next step? The next step is to calculate expected frequencies. So expected frequency of a cell is row total multiplied by column total divided by grand total. So here we are going to calculate the expected frequencies of these cells. So these are the observed frequencies, and these are the row totals 303 and 302. And what are the column totals? The column totals are 22, 38, 33, and 512. So expected frequency for the first cell, which represents cancer cases on AHA diet. So the row total for this cell is 303 and the column total for this cell is 22. And they are multiplied and then they are divided by the grand total, which is 605. The expected frequency is 11.0182. Now the observed frequency for the cancer cases on Mediterranean diet is 7. But this observed frequency right now has nothing to do directly with the calculation of the expected frequency. So what do we need to get the expected frequency? We need to get the row total and the column total. And the row total here is 302 and the column total here is 22. So we have 302 multiplied by 22, and then their answer is divided by the grand total, which is 605. The expected frequency is 10.9818. Then the next cell, we have the non-fatal heart disease cases on AHA diet. The expected frequencies are row total 303 multiplied by the column total 38, and then they are divided by the grand total, which is 605. The expected frequency is 19.0314. And then we have the non-fatal heart disease cases on Mediterranean diet. So the row total is 302 and the column total is 38. They're multiplied and then their product is divided by the grand total, which is 605. So we have the expected frequency 18.9686 here. And then we have the next cell, which is the cases of fatal heart disease on AHA diet. The row total in this case is 303 and the column total in this case is 33. And then they are multiplied and then the product is divided by the grand total of 605. So the expected frequency is 16.5273. Then we have the next cell, which is the fatal heart disease cases on Mediterranean diet. The row total in this case is 302 and the column total here is 33. They are multiplied and the product is divided by 605. And the answer is 16.4727. Then the next cell is of healthy individuals on AHA diet. The row total is 305 and the column total is 512. They are multiplied and their product is divided by the grand total, which is 605. And the answer is 256.4231, which is the expected frequency of healthy individuals on AHA diet. Now in the last cell, we have the healthy individuals on Mediterranean diet. And the row total in this case is 302 and the column total here is 512. They are multiplied and then their product is divided by 605, which is the grand total. So we have our expected frequency of 255.5769. So this is how we calculate the expected frequencies. So here we are with the calculation of the chi-square value, again with the same table. So the observed frequencies and the expected frequencies are given in the first two columns, and their sum, their total is same, which is 605 in this case. And all the categories are also given here: Cancer AHA, Cancer Mediterranean, and so on. So what is the next step? We have to calculate the difference between the observed and expected frequency of each cell. So the first cell is Cancer AHA. The observed frequency is 15 and the expected frequency is 11.0182, and their difference is 3.9818. And the next cell is 7 minus 10.9818, which is the difference between the observed and expected frequency of cancer cases on Mediterranean diet, and the difference is minus 3.9818. And then the next cell, which is the non-fatal heart disease on AHA diet, and the difference between the observed and expected frequencies is 4.9686. And then for the next cell, this is non-fatal heart disease on Mediterranean diet. The observed frequency is 14 and the expected frequency is 18.9686, and the difference is minus 4.9686. The next class is the fatal heart disease on AHA diet. The difference between the observed and expected frequency is 8.4727, and then the difference for the next cell is minus 8.4727, and the difference in the observed and expected frequency of the last two cells of the healthy individuals, so this is 17.4231. So this is how we calculate the difference between observed and expected frequencies. Next column is about taking the square of difference between the observed and expected frequencies. We are following the same procedure. We are taking the square for each cell. 3.9818 square, which is 15.8547, and then the square of difference between the observed and expected frequency of each cell, right? So after we have taken the square of difference between the observed and expected frequency for each cell, we are going to divide that square of difference by the respective expected frequency. So 15.8547, which is the square of difference between observed and expected frequency of cancer AHA, is divided by the expected frequency of the same cell, which is cancer AHA, and the result is 1.439. Now we do the calculation for the next one. This is 15.8547, which is the square of difference between the observed and expected frequency of cancer cases on Mediterranean diet, and they're divided by the expected frequency of the same class of the same cell, and this is 1.4437. And then 24.687 divided by 19.0314, which is the expected frequency of the same cell non-fatal heart disease on AHA diet. We calculate that for the next cell as well, which is non-fatal heart disease on Mediterranean diet, and the square of the difference between observed and expected frequency is 24.687, and this is divided by the expected frequency, and the result is 1.3015. So we do the calculation for every cell, and finally we are going to do the calculation for the chi-square, and chi-square is simply the sum of this fraction, which is the square of observed and expected frequency difference divided by the expected frequency. The sum of 1.439 plus 1.4437 plus 1.2972 plus 1.3015 plus 4.3435 plus 4.3579 plus 1.1838 plus 1.1878, and the total is 16.554. So this is the value of our chi-square. What is the next step? Calculate the degree of freedom, and the degree of freedom for the chi-square test of independence is number of rows minus 1, number of columns minus 1, which in this case is 2 minus 1 and 4 minus 1. So 1 multiplied by 3 is 3. So 3 is our degree of freedom in this case. Consulting the chi-square table, so 3 is our degree of freedom, and what is the level of critical probability that we look at? It is 0.05, and the table value is 7.815. So our calculated value is 16.554, which is much greater than the tabled value. So what we are going to do with the hypothesis, with the null hypothesis, are we going to accept it or are we going to reject it? So we are going to reject the null hypothesis because the probability of null hypothesis to be true is less than 0.05. Therefore reject it, and this result is significant. We accept the alternate hypothesis. Now what is the next step? Once our null hypothesis is rejected, we want to see that what is the maximum level of significance that we have for this rejection of the null hypothesis. Next level is 0.01. 11.345 is the table value. Again, we see that our result is highly significant because calculated value is greater than the table value. And then we see the next level, which is 0.001, and here we see 16.266, and this value, although it is very close to 16.554, but it is still less than 16.554. So this again emphasizes that you have to take in maximum number of digits after decimal point that you can, so that you can have an accurate result. So 16.554 is greater than 16.266, so we are going to say that our result is very highly significant. So chi-square value is 16.554, degree of freedom is 3, the table values are 7.815, at probability of 0.05, at probability of 0.01 it is 11.345, at probability of 0.001 it is 16.266, and our calculated value is greater than all of these values. So we are going to say that there is a very highly significant association between diet and health status. So chi-square is equal to 16.554 and probability is less than 0.001. That is why our result is very highly significant. So I think this is clear. Now it is time for the assignments. I know assignments are boring for you, but still obviously you have to do the assignments so that I can assess that how much you have understood from this topic. So what is your assignment in this case? The assignment is that you have to pick up at least 2 examples, either from the daily life or from biology. So I prefer examples taken from biology because you're studying biology course, but you can take example from the daily life as well. But out of the 2 examples, at least 1 should be from the biology, right? So you have to take 2 examples for each type of the chi-square test that you have studied. So how many chi-square tests that you have studied? These are chi-square test of homogeneity, chi-square goodness of fit test, and the chi-square test of independence. So you have to take 2 examples for each. So total number of examples should be 6, and this is a minimum number. If you want to put more examples, so you're highly encouraged for that, because that is how you can assess your understanding of the subject, that whether you have understood the chi-square concept pretty well or no. Because you know, the main purpose of statistical analysis is not to do these calculations on paper. The main purpose of this course and the main purpose of a biostatistician is that you have to understand that what kind of a statistical test you are going to use. So the choice of statistical test is what makes you an analyst, what makes you a researcher. This analysis can be done on the paper, this analysis can be done on the softwares, but unless and until you know that what kind of the test do you actually need, there is no use of making any kind of analysis, of doing any kind of analysis, of doing any kind of a test. So that is why it is important that you sort out the type of the question you have and the type of the statistical test that you have to employ. So these are your assignment instructions, and again, you don't just have to give your examples randomly. You have to follow the proper scientific format for this purpose. The same way you can report your experiments in your lab journal. So what you have to do is you have to write down a question. So first of all, you have to write down the question, and then you have to state your null and alternate hypothesis. So you have to come up with a proper null hypothesis, a proper alternate hypothesis for the question that you are asking. This is very important because you have to understand the concept behind it. And then you have to decide that what kind of the chi-square test you are going to use. Are you going to use the chi-square test of independence, chi-square test of homogeneity, or chi-square goodness of fit test? So you have to apply the appropriate test. And then you have to give your results according to the question asked. So remember one thing, that calculation of the chi-square value alone, the calculation of test statistic alone in any kind of statistical analysis is not sufficient. You have to describe your results according to the question that you had put, right? So you had put a question, you did a test, you did an experiment. In this case, experiment is statistical analysis. So you did that experiment to find out the answer to your question, and you had followed the method of hypothesis testing for that purpose. So you have to give your results according to that. You don't have to give the results that my chi-square value is 2.15. No, that is not an answer. You have to state that what is your result according to the question, right? So stating the result is more important. So calculation of chi-square value is not enough. Similarly, that will also be applicable in your exams as well, not just in assignment, in the exams as well. So if you are given a question which involves the chi-square test or any other statistical analysis, you have to give your result statement. So result statement will have its own separate marks. Even if you have done exact calculations, you have done very fine calculations, and your answer is exactly as what it should be, still you're not going to get the full marks. You did the correct calculations, still you're not going to get the full marks. Why? Because you didn't give your result statement. You are a researcher, you are not a technologist, right? You are not a technician that you are going to just calculate things on paper and give a number. No, you have to analyze the things, you have to analyze the problem, and that is your training. So you have to come up with your result. So this is your assignment.